We realize that a reservoir rock is normally saturated with at least 2 and sometimes 3 fluids: water, oil, and gas. The relative amounts of these fluids present, their composition, and physical properties, such as their phase behavior, density, viscosity, and compressibility, can vary widely from field to field and often from reservoir to reservoir. During production, the fluids leave the reservoir at whatever its conditions are at the time and flow up the tubing and through the surface facilities. Let's look at this on a plot of pressure versus temperature.
Initially, the pressure-temperature path followed by the fluids is between original reservoir conditions and stock tank conditions. Later, after some production has occurred, it is from a lower reservoir pressure. In order to manage our reservoir properly, we need to know how the fluid properties change both in our reservoir and as they come to the surface during production. Natural gas is the easiest to discuss. Gas expands as the pressure is reduced and contracts as the temperature is reduced. As an example, a gas with a specific gravity of 0.7 relative to air, at a reservoir pressure of 5,000 psi and a reservoir temperature of 200 degrees Fahrenheit, will expand by a factor of about 270 as it comes to surface conditions. Of course, this figure will change as the reservoir conditions or gas gravity changes. Crude oil behavior is much more complex than the behavior of a dry gas. Let's assume we have a sample of crude oil, that we take it to the laboratory, place it in a sample chamber, and restore it to its original reservoir conditions of temperature and pressure with a mercury pump. We look through the cell window and see that it is all liquid. The conditions of the sample are represented by point A in the PT diagram. Now we slowly drop the pressure. Suddenly, a bubble of gas appears in the crude. We are at the bubble point, that is the point where 2 phases begin to be present. We continue to decrease the pressure, the total volume expands, and more of the total volume is gas. In fact, when gas was first formed, it consisted of the very lightest molecules, perhaps methane. Now, because of the lower pressure, more and more of the heavier molecules move to the gas phase, causing it to become more dense and more viscous. The oil, having given up lighter hydrocarbons to the gas phase, has also become more dense and more viscous. Finally, we reach the point where only a small drop of liquid remains in the chamber. This is the dew point. Once we drop the pressure to a lower value, the liquid disappears and everything is in the vapor or gas state. Between the bubble and dew points, then, we have 2 phases present. This is known as the 2-phase region. If we repeat this experiment on the crude oil at a number of different temperatures, we will find new bubble points and dew points at each temperature. We can now join these points, obtaining the bubble point and the dew point lines. The curves join at the critical point. Between the curves, we have the 2-phase region, above it only liquid, below it only gas. Within the 2-phase region, we can join points of equal percent liquid. Each crude oil has a different phase envelope, but for simplicity, the reservoir engineer will often define a broader classification range for crudes. This classification may depend, for example, on composition, gravity, and gas-oil ratio. Here we see a 4-group range, beginning with a dry gas. Then, as the hydrocarbons get heavier, we have a condensate, volatile oil, and black oil. Note that the methane content drops as the hexane plus fraction increases. We may now look at the phase diagram for several of these fluids. Here we see the diagram for a dry gas. Now we introduce the reservoir and surface conditions and draw a line indicating the probable production path. Note that fluid never enters the liquid state during production. For a condensate, we see that 2 phases will form in the reservoir as we drop the pressure, and that a small percentage of liquid will be recovered in the separator. For an oil, we may start off with only liquid, but a gas phase will form in the reservoir as the pressure is reduced. We also see that as production flows to the surface, more gas will come out of solution and be separated in the separator. Remember that as we reduce the pressure, the volume of crude oil and any free gas that is formed increases, and this is especially significant at pressures below the bubble point when gas is present. The oil itself expands as pressure drops to the bubble point pressure, and then decreases in volume as free gas comes out of solution. A barrel of original oil in the reservoir, then, will be a smaller oil volume in the stock tank, but the total volume of both oil and gas that came from the original barrel will be larger. Just as the phase behavior of different hydrocarbons varies, so also does the density, viscosity, and compressibility. Gas and oil densities are normally expressed as specific gravities or API gravity. Some examples of crude oil API gravities are shown here. Note that the range of values is quite wide, from heavy crudes with values close to that of water to light crudes with gravities in the 50s. Gas-specific gravities range in magnitude from about 0.6, which is pipeline quality, to 0.9, which represents a rich gas containing condensate. Gas is much lighter than oil, and so it will tend to move upward in a reservoir under the force of gravity, while oil moves downward. The crude oil viscosity will be higher, that is, have a heavier internal resistance to flow for a heavy crude and lower for a lighter crude. We can reduce the viscosity of a crude by adding lighter hydrocarbons to it or by increasing its temperature. Compressibility is the amount that a unit volume can be compressed per unit pressure increase. Of course, it is also the amount that a unit volume will expand per unit pressure drop. Its units are volume per unit of pressure, or 1 over the pressure unit. Compressibility can be a very important reservoir drive mechanism because the expansion of fluids as a reservoir pressure drops contributes significantly to production. We see here an example of some average compressibility values. Note that gas is much more compressible than reservoir liquids, and thus will expand more as pressure is reduced.